We start today with our lecture in business intelligence on 17th of October 2024, and I am going to ask you again for the last time, when we do our lecture online, please be 5 minutes before the lecture there, okay? Otherwise it's difficult. Today we will look at starting to learn the fundamental basis of what we call today artificial intelligence. So the very basics, and I have called this lecture Deep Learning by Hand. Okay? So we are going to do deep learning with a piece of paper and a pencil, which is the way to learn it, in my opinion, okay? The way to understand what goes on when we do what we do. So before we step into deep learning, which has different layers and stuff, we need to start explaining what a single neuron does. That's why we start with something called perceptron, and the easiest perceptron is a single neuron. Perceptron. Okay, so basically we have our computational unit, which is one big ball that is going to perform following task. It gets certain sets of inputs, x1, multiplies the input with a weight and puts the input into the neuron. And we do that for several inputs. And when we have n of these inputs, as I said, an input multiplied by a weight, what this neuron does is it adds up all the multiplications neurons time weight. This is called the perceptron. And then we go and create another computational unit, which is called activation function. And then we measure the output. We measure here the output, and put it back into the weights to initialize again the weights. So we actualize the weights and create a feedback loop that is going to measure or adjust the weights when we do it. So let's go through this cycle in, let me put it again in a different way. So we have a vector of inputs. We have a vector of weights. We have our neuron. We have our activation function. And we have our error that actualizes the I guess I'm missing here a minus. Yeah, and this actualizes the weights, and at some point we find the optimum of the weights. Okay, so the step one, let's talk about this step by step, is multiply all input values xi with their corresponding weights wi, and then calculate the weighted sum okay. The function we will call f. The step two is apply so as of next week, when we start the lecture, I don't let anybody in, okay? An activation function is applied to the above giving an output of the form y equals f of the sum plus an error or a bias. Okay, let me put a bias b. This has the form of like this if we only have 2 dimensions, okay? This is the line and the bias translates the line to some other latitude, moving it, okay? So we will use an activation function here. There are many, and you can look for them. Examples examples of activation functions are the step function. Step function looks like this. Zero whenever x is smaller than 1, than 0, and some sort of step, usually 1, otherwise. So f von x is 0 for x smaller than 0 and 1 for x bigger than 0. This is the step function, but we don't use this. This is not very good. What the activation function that we are going to use is called rectified linear unit, or in short, ReLU. And this function looks like this. This function looks like following. So if this is x and this is y, we have 0 for x smaller than 0 and y equal x for x bigger than 0. So f von x is 0 for x smaller than 0 and x for x bigger than 0. This very simple function helps us very well. It can be computed very easily, and it's yeah, super effective for our purpose. So we have step 1, we have step 2. Any questions so far? Step 1 deals with this part. So this is basically step 1. Now let me use other color. So we have step 1, which goes here, okay? This is step 1. Then we have step 2. The activation function. Okay. And then we're gonna have step 3, which is going to be the error correction. Okay. Any questions So far with step 1 and step 2. I guess we can call this y with hat. So step 3 is about calculating the error. So we need to calculate the weight values which make the equation y with a hat of the sum of the weights times xy plus the bias vector as similar as possible to a prediction. So I guess one way to put it is that here you have your y with a star with a hat, and the goal is to make this y with a star and the y prediction as similar as possible. Okay. For this, we use the quadratic of the difference between the two values y minus y with a hat, which is the error. Okay, being y the prediction, and being y with a hat the calculated value. So we measure how far off we are. This quadratic difference is called the quadratic error. Okay, and we divide it by 2 so that when we want to let me first say something about the quadratic error. We divide it by 2, but let me first say that the quadratic error is called cost function, and it's called 1 divided by 2 y minus y with hat square. So let's explain this equation in detail. Explanation. The error y minus y with a hat is squared, so that all values are positive. They don't cancel each other. Okay. We divide it by 2. Because we want to find the minimum of the function c, and for this we will find the first derivative of the cost function, and as you know, the first derivative of something square is 2 times the function. That's why if we multiply it with 2, so to find the minimum of the cost function, we use the first derivative. Okay, so because in the minimum the first derivative is 0, as you already know. So the cost function, as I said, is 1 divided by 2 y minus y with a hat square. Now we know y. This is 1 divided by 2 y minus b square. Okay, we call this function error or cost. That's why the c. And we want to find the values of w, which is w1, w2, wn, that minimize the cost. Okay, so in order to do so, what we do is we are going to derivate. It's a multi-variable function. We have w1, w2, all the variables, and this is, now you will see why we are dividing by 2. 1 divided by 2 times 2 times y minus w1 x1 minus w2 x2 minus minus wn xn times the derivative of the function with w1, which is minus x1. Okay, the derivative of this function regarding to w1 is minus x1. That's why we do it like that. And then for the rest is the same. Y minus times minus x2 So this set of equations help us find the minimum values of W vector to minimize the error, the cost function. And this set of equations, these derivatives, are called gradients. Okay. Is this understandable? Any questions? We will do an example later, yes. Yes, yes, we will do examples, yes. We first need to explain the theory. Yeah. First the theory and then we do examples. So, these derivatives are called gradients. Any questions on this step number 3? So we have now step number 1, step number 2, step number 3, and then we now need to roll and perform several loops here, okay, to I will paint it in, we do several loops, okay, and the loops are called something that is called gradient descent. Okay, something called gradient descent, which is the step 4. And basically, this is just initializing the weights and then changing the weights so that we optimize them. So to reach, in order to reach a minima in the cost function, we will start taking small steps in the direction of the minima, okay, which is the opposite direction of the gradient. We do so by updating the weights. Okay, by a small amount. This amount is called learning rate. Okay, so if the cost function is something like this, of course this is multidimensional, I'm just going to paint it in one dimension. If the cost function is like this, what we do is we update the weights. We are somewhere here in the beginning with the initialization, then we update the weights, and then maybe we move there, then we move there, we move there, and at some point we reach the minima. Okay, so any questions on step 4? I have color coded the steps so that you can follow them in the image above. Okay, so step 1, step 2, step 3, step 4. I guess step 4 I need to write still. Any questions before we start with one example? So what we called, or what we have here, step 1 and step 2, okay, goes in one direction, and then step 3 and step 4 goes in the opposite direction to update the weights, right? So if we paint that again here, we have a vector of an input that is multiplied by a vector of weights that goes into some sort of thing that puts it together. Then we have some activation function that jumps into one calculation, and we bring that back with our cost function, and we perform that many times until we reach a minimum of the cost function, and those are the optimum weights, right? So there are two steps here, or two directions. One direction is that way, and this way is the feed forward process. Okay. This is the feed forward process because it goes in one direction. And the other process, as I said, goes in the other direction, and this is backward propagation. Of the weights, okay? And this is the nomenclature that we will be using: feed forward and backward propagation. So, questions so far? So this is the basic process that deep learning follows. And if you understand this deeply, you will understand what deep learning is about, which is the basis of almost all artificial intelligence processes that we know today. Okay, this process is based on the studies of some neurologists in the 1960s on the visual cortex of cats. Okay, so then mathematicians started playing with this model that some neurologists saw. That's why it's called neuron, and that's why we call it learning, because it's artificial based, artificial neurons. Mathematicians started developing all these models, and what we have today, and the reasons why ChatGPT works, and the reason why your telephone is able to recognize your face and stuff like that, is this process. Okay, this is the very basic, just with only one neuron. Okay, so we could finish the lecture here, and you would be able to take any book on deep learning and understand the rest. But yeah, let's no, that's just a joke. Let's continue with some examples. So example number 1, it's called single neuron perceptron forward pass. Okay, so we take and we do the forward pass, this part, step 1 and 2. Okay, and for that we are going to take a vector of 3 elements. They're going to be 2, 1, and 3. Two, 1, and 3. This is, of course, x1, x2, x3. Okay. We're going to take a weight vector. No. So our weight vector going to be 1 minus 1, 1. 1 minus 1, 1. And we're going to take a bias, which is going to be minus 5. And I put that there. And you will see why I do this. So this is, as I said, W1, W2, W3, W1, W2, W3 on the bias. And this is X1, X2, X3. Okay. And what we have done today, if you remember, is we have calculated y with a hat. Okay, so y with a hat. Y with a hat is going to be the activation function applied to the sum of the products plus the bias. So here we will calculate this part. Okay. And then we will apply our function, our activation function, and we will get our y with the hat. Okay? So we have said our activation function is the ReLU. ReLU is 0 for x smaller than 0 and x for x bigger than 0. Any questions on this setting? I need you to give me feedback. Yes, no, I don't give a fuck, whatever. Give me some feedback, please. Are you there? Hello? I didn't hear the rest of the question. Du kannst gerne in Deutsch fragen. Hello? Yeah, now I can hear you. Can you ask in German, please? Ja, ja. Ja, du siehst es gleich. You're asking, let me translate for the rest. You're asking, the first thing we do is we calculate this, okay? Then we apply the function, okay? And then we get the result. You will see it is super easy. You don't need to be scared about this being hard mathematics. This is really not hard mathematics. What you need to do is be alert and make sure you follow every step. And if you don't understand any step, you say, stop, please explain again, okay? Just as you're doing. So let me write the same, y. No, I'll do it, I'll do it here. Is the function of 2x1, I'll put it here, w1 times x1 plus w2 x2 plus w3 x3 plus the bias, okay? This is just the same as before. And well, let's do that. F W1 is 1 times x1 is 2 plus W2 is minus 1 times 1 x2 plus W3 1 times x3 3 plus minus 5 equal. So if somebody in the exam adds 2 and minus 1 and then multiplies by 1, I don't read the exam anymore, okay? You get a 0. Because this is something from 3rd grade, okay? I saw that last year and I was like, what the fuck? So 1 times 2 is 2, minus 1, plus 3, minus 5. That's why, I mean, this is deep learning with a hand, because we don't even need a calculator. 2 minus 1 is 1, plus 3 is 4, minus 5 is minus 1. And because we have a ReLU, and minus 1 is smaller than 0, this is equal 0. Okay? Is it understandable? I don't know who asked, but is it understandable? Yeah. What was that? I don't get it. Can you ask again, please? Yeah, of course. Ja, weil hier, wenn x kleiner 0 ist, dann ist die Funktion 0. Und ja, dann ist x. Dann ist die gleiche Zahl. Ja. If f von 5 ist gleich 5. Ja. Ja. Die the our Rilo rectifier linear unit function is like this: x and y. So here we have 0 and then x, okay? So if the number here is smaller than 0, then it's 0. If the number here is bigger than 0, then it has the same value. Okay? Hallo? Also, verstanden jetzt. Ja. Any questions? So I like to do it also graphically. The same thing we did now with numbers. I like to do it graphically. Is 2 times 1. Okay? Or 1 times 2. And I guess I'm going to take another color. 2 times 1. 1 times minus 1. And 3 times 1 plus the bias. Okay. This equals minus 1. And because we apply ReLU, this equals 0. Here, no, here, this equals 0. Okay? Any questions so far? I need feedback. I need yes, no, thumbs up, thumbs down, something like that. 2, 3, 4, 5, okay. Okay, so nobody asks, I only see thumbs up. So this is the first example of your life, maybe, about deep learning. And I think this is the best way to learn it, okay? I could start here with super complicated examples like image recognition examples. This is how they explain it in the informatic faculty, you know, but I think it is better to start like babies when learning something like this. If you start with like babies, you then later on understand the things for boys, and then you can grow up to the real hard stuff. So if you don't have questions, I go to the next example. May I go to the next example? Okay, so now thank you. We go to example number 2. Now we don't have only one neuron. Now we will have 2 layers of perceptrons, okay? One with 3 neurons and one with 4 neurons. And this is going to be a little trickier. So the exam question last year was think about this a little bit more complicated. So calculate the output of 2 layers of perceptrons with 3 and 4 neurons respectively. Okay? So let's make a picture. I always believe that if people see things in pictures, they understand them better. Let's take the first layer with 3 neurons. Okay. The second layer with 4 neurons. Okay. We want to calculate our y with a hat. So the vector is going to be y1 with a hat, y2 with a hat, y3 with a hat, y4 with a hat. So each corresponding to, each neuron. And then we also have a vector here, x being x1, x2, x3, the input of each neuron. And then we have a weight, okay, connecting all neurons to each other. So here we have a weight connecting neuron 1 of the first layer with neuron 1 of the second layer, and then connecting neuron 1 of the first layer with neuron 2 of the second layer, and neuron 1 of the first layer with neuron 3 of the second layer, neuron 1 of the first layer with neuron 4 of the second layer. And the same thing for all relationships throughout the layers. So it takes a little bit time to do it, but I think it's nice thing to do to represent it smoothly, so I'll take the time. Basically, this is what is called a fully connected multi-layer perceptron. All right. It's a fully connected multi-layer perceptron. Fully connected because everybody is connected with everybody else. Multi-layer perceptron. All right. And as I said, this is going to be a game of updating the weights. We will just do the feed forward pass, but this is weight 1, 1 because first neuron of the first layer, first neuron of the second layer, and this one's called 1, 2, and so on. Okay. So let's describe how this works. And I need here Blackie. Well, and this you understand the logic, right? So this one is called weight 2, 4. Okay, because it's second node, second neuron of the first layer, fourth neuron of the second layer. This is called 3, 3, and so on. Okay. So any questions so far? Yeah, it will be a matrix. Yeah, exactly. It will become a matrix. You'll see in a minute. Exactly. So we go there and we describe now the problem, and this is what you would get in the exam as well. Okay. You would get some numbers. You would need to put these numbers into order and understand what the fuck you're doing. 2, 1, 3. Okay. This is x1, x2, x3. And then we get our weight matrix with the bias. It takes some time to put it neat. I could do it faster and wouldn't be so nice, but I think it's better for learning if it looks more clean for your learning process. So that's why I take the time, okay? It's like in the army, fast is slow and slow is fast. So the weights are going to be 1 minus 1, 1 minus 5, 1, 1, 0, 0, 0, 1, 1, 1, and then 1, 0, 1 minus 2. And then this is just it's gonna be my So this part are the weights. It's the weight matrix, and this column is the bias. Okay. So this is the bias, and this are the matrix elements, being the matrix being weight 1 1, weight 1 2, weight 1 3, weight 2 1, weight 2 2, weight 2 3, weight 3 1, weight 3 2, weight 3 3, and weight 4 1, 4 2, 4 3. Okay, which is nothing else but what we describe here in the relationships between the nodes. Can you follow so far? You, of course, reckon we have dimensions of x is 1 times 3. Dimensions of w is 3 times 4. Dimensions of b is 1 times 4. So if we want to calculate all this, we want to do it taking the dimensions into consideration. That's why we do it in a graphical way. It's way easier, in my opinion, to understand. So once we perform that, once we perform it, we apply ReLU. And we get the result we're looking for. Okay. Any questions? Let's do the calculation then. 2 times 1. Well, I'll do it first. I'll do it with numbers. So I get the sum of wi xy plus b. Okay. Then apply the function, which will be something like the vector 2 1 3 multiplied by 1 minus 1 1 1 1 0 0 1 1 and 1 0 1 plus the vector of b 0 minus 5 0 1 minus 2. Okay, so let's do it. 2 times 1 plus minus 1 times 1 plus 3 times 1 minus 5. I'm doing 2 times 1, 1 times minus 1, 3 times 1, minus 5. If you want to follow, you can follow the video later. And this is 0. Then I do again 2 times 1 plus I guess let me put it in right order. 1 times minus 1 to follow always the same order. 1 times 1 plus 3 times 0 plus 0. Okay, so it's 2 times 1, 1 times 1, 3 times 0 plus 0. This equals 3. So 3. Then we have 2 times 0 plus 1 times 1 plus 3 times 1 plus 1. This equals 5. And then 2 times 1 plus 1 times 0 plus 3 times 1 minus 2 equals 3. Because all the elements are positive, our last, after applying the ReLU, is going to be in this example. So, were you able to follow? Was I too fast? I can repeat it as many times as you want. This is relevant for your exam. I guess this calculation is this calculation, okay? Sure. Enough. No problem. You will need to train yourself to go fast. Okay, so I assume that when you go to the exam, you will have not only understanding, but you will also have practice. I repeat it in German. It's important. Manche Studierende klagen, dass es zu wenig Zeit gibt für die Prüfung. Das ist auch bewusst so. Ich möchte nicht nur wissen, wer die Dinge gelernt hat, sondern wer auch ein bisschen gearbeitet hat. Okay? Es reicht mir nicht zu verstehen, es muss auch in der Zeit gemacht werden. Is your question answered, Jürgen? So I'm sorry, but what I want is that you guys, so you can go ahead and give yourself new numbers, okay? And instead of doing 3 times 4, you can do 5 times 6 and see what happens. And this will help you understand what dimensions, where to put, okay? So you can do it yourself. You are already in your 3rd year of studies, so you can do that, and I'm sure you will succeed in doing that, okay? If you want to get more practice, you can do it yourself. So I just translate the exercise numbers. We could do it also here. I think by doing this graphically it's easier, and I will also ask you to give me the answers in such a format in the exam. Okay? Wait, I think I made a mistake here. It's -1. 2 -1 is, yeah, it's -1. So this is -1. And because it's a ReLU, it translates into a 0 later on here, okay? So, yeah, this is the way to do it properly. Any questions so far? This was only, let's say, this was only the forward pass. Still, we need to learn how to do the back propagation. Okay? This is only, as I said, the forward pass. So you are right now learning how to do artificial intelligence, okay? So this is the basics. Of course, this is super easy, and but this is the basics of business intelligence, what we understand today as business intelligence, okay? Deep learning. Probably the technology of the future, if not of the present. Nobody explains that into your studies so far, I think. Is this new for you? You can open your microphone. I cannot see your face. So this is new. You have not seen it before, right? In any course, in any lecture. No. Somebody saw this in the studies. Okay, so this, as I said, this is just the basics. It's the first step, the first stone of your artificial intelligence, business intelligence course. It's a cornerstone of artificial intelligence, deep learning, and it's the technology of the future. So make sure you learn this very, 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 very good, okay? Anyway, we'll stop the video here. We continue our exploration of deep learning with by hand with example number 3, which includes a 3-layer perceptron, always still forward pass. And the 3 layers are 3 neurons, 4 neurons, 2 neurons. Okay? So this is the way to put it in the nomenclature. So now I go a little bit faster, as you can imagine. So we have our initial input vector 213 again. Okay, so this is x1, x2, x3. Then I have my neurons again, 1, 2, 3. Then 1, 2, 3, 4. And also 2. Okay. So that in the end we will have a vector here, an output vector of I1 and I2 with a hat. And the middle layer is what we call, so this is X, okay? X1, X2, X3. And the middle layer is what we call a hidden layer, okay? H. So this example, it's called hidden layer perceptron, okay? Again, everything is connected to everything else in the next layer. It takes time now, again, to connect everything with everything else, but I think it's important for the didactic. It's like I mean, for me, with a woman, for maybe for the girls with a man, fast is slow and slow is fast. So you want to take time to make things right, okay? And this is how we learn here. We don't leave anybody back. So if somebody has a question, don't hesitate to ask. Manchmal is my sometimes is my answer seems to be a little bit rough or unfriendly, but it's just the tone. I don't mean it like that. It's just that I am in my tunnel thinking of the next 4 steps, and that's why. But I am very happy to answer. Anyway, so we continue there, connecting everything with everything else of the next layer. So we have our weight matrices set up, and the next step will be to put the numbers in place. So one example so that you can have, it looks pretty, I think. And so let's look at the, not pretty enough, as pretty as it gets, I guess. So let's try a line there in the middle, duplicate, so we get our weight matrix. And then we get our horizontals as well. So the dimension of our weight matrix is again going to be 3 times 4. This is going to be our weight matrix from 1 to h, and this is our bias 1. Okay, so let's put it 1 minus 1, 1 minus 5, just as before. So we can go faster there in the calculations. 0, 1, 1, 1, 1, 0, 1 minus 2. And what we are going to be getting as well is another matrix somewhere here. So as I said, this has dimensions 3 times 4. This has dimensions 1 times 4. And our new, let's say, weight matrix for the next level between H and 2 will be like this. Again, a little weight matrix. Can somebody tell me the dimensions of the weight matrix here? Hello? Before I paint it. For 2. Yes. Very well. So our weight matrix 2H has, or H2, I guess, H22 has dimensions 4 times 2. Our bias 2 has dimensions 1 times 2. Okay, so and here we need again some numbers. I'll just put some random shit. Is 0, 0, 1, minus 1, 1. And then I will ask you in the exam, please calculate I1, I2, the vector, which is going to be something like with dimensions of what? One, 2. Thank you. In order to get there, we need a ReLU, rectified linear unit. In order to get the ReLU, we need to multiply the output of the hidden layer again and the output of the hidden layer. We already know how to calculate it. Because we have done it above, so I will not repeat. 0, 3, 5, 3. And now the output, this is the output of the hidden layer. And now we need to calculate that with the second layer. So what we do is we again apply ReLU to the weights H2 to the hidden layer plus the bias 2, which means is applying ReLU to something like this. 1, 1, minus 1, 0, 0, 0, 1, minus 1, multiplied by 0, 3, 5, 3, plus 0, 1. Okay, I'm just copying the numbers above. And that's going to be like 1 times 0 plus 1 times 3 plus minus 1 times 5 plus 0 times 3 plus 0, which turns out to be minus 2. So here we get vector minus 2, and then 0 times 0 plus 0 times 3 plus 1 times 5 plus minus 1 times 3 plus 1. This turns out to be 3. And then this is going to be turning out to be 0, 3. So we copy that there. Minus 2, 3, 0, 3. All right. Again, it's just like multiplying 1 times 0, 1 times 3, minus 1 times 5, 0 times 3 plus 0, and 0 times 0, 0 times 3, 1 times 5, minus 1 times 3, plus 1 equal 3. If you have issues following, just look at the video, you will see the sequence there. Any questions? Well, whenever you ask a question, I don't know who is asking. What's your name? Finn. Finn, whenever you ask a question, don't start your question with the word but or aber, because that doesn't sound good in the guy listening. So rephrase with and, okay? I don't. Yeah. With input, you mean this? Yeah, of course. Yeah. You can get a matrix, but instead of getting a one single number here to the neuron, you get a vector, okay? And then you go from there, but then you don't have a perceptron. Then you have something different. We are going in baby steps here, okay? So yeah, but of course you can have a vector, you can have a tensor, you can have, as we saw in the first lecture, an image in color is a 3-dimensional matrix in reality. So in order to do deep learning to images in color, you need to input not numbers, but you need to input a matrix. So this would work, for instance, if you work with black and white images, okay? That's how it works. This is very simple, very just for the first steps, okay? Any more questions? So No questions? Are you sure? Okay, so so far we have seen the feed forward process. Now we're going to have our feed forward and back propagation. So perceptron with hidden layer. It's going to be 3 times 4 times 2 times 3 with feed forward and back propagation. Okay. For that, we need to learn a little one thing more, which is the concept of softmax function. If you get a vector of, let's say, x, let's say 2, 1, and 3, and you apply softmax, let's say softmax to this vector, then the elements of the vector are going to be proportional to the elements of the previous vector, but they're going to all add up to 1, okay? So the sum of all elements is going to be 1. So you get 2 divided by 2 plus 1 plus 3. 1 divided by 2 plus 1 plus 3. And 3 divided by 2 plus 1 plus 3. Yeah, wait until I finish 1 second. So this is going to be 1 divided by 2 divided by 6. 1 divided by 6 and 3 divided by 6, which is proportional to the original, but the elements add up to add up to 1. So please go ahead with your question. It doesn't matter. So this is the softmax function, okay? And this is what we need to, because this is going to be our decision layer. Okay. So let's let me give you the example. We have our input vector to let me do it nicely. We have our input vector 2, 1, 3. Okay, so our first layer is going to be of 3 neurons, as I said. Then we have our first layer. Our first layer there. The matrix of the weights. is going to be like this. The weights and the bias, I guess. This we already know. I am always taking the same numbers, so I don't need to do the calculations all the time. But of course, you should try to use different numbers for your own benefit, okay? So this is the weight 1H, and this is B1. I guess this is the first hidden layer with 4. First hidden layer. Okay. With 4 elements. So now I get a second hidden layer with 2 elements. And then our output layer with again 3 elements. And then I have my output vector here with y1, y2, y3. In our feed forward, so this is our setting. Let's get the numbers for the example. And here I have 1, -1, 1, 0, 0, 1, 0, 1, -1, 1, 3. Okay, so this is the second layer, the second hidden layer. And these are the weights from the first hidden layer to the second hidden layer. This is B2. The output there, the output of the first I guess I need some space in between. I need here some space in between. So I'll leave it. Yeah, that's better. Just copy the same. -1, 1, 0, 0, 0, 1, -1, 1, 3. This is weight H1, H2, and B2. And I also need some space here, so I'll move it up. To 1, 3. This is our input. All right, so that's our setting. This we don't know, that's why I painted in, let's say, red. We don't know yet. And also here, we then have a ReLU, rectifier linear unit, and the feed forward we already know how to do, so I'll just go fast on that. I could have this, I could have prepared this before, but if I prepare it, the problem is that you don't see how it happens, and then we lose some didactic edge. That's why I don't prepare it. I do it 100% in front of your eyes, okay? So the output of the second hidden layer is 2, 1, okay? And then we have our last weights, which are given. Again, I need some space in between. And then this is going to be like this. And like this. 2, 0, minus 1, 0, 2, minus 5, 1, 1, 1. This is going to be the weights between H2 and 3, and this is going to be B3. And then there's going to be an output there, which is going to be like this. Once we perform the feed forward, then we do some softmax. And this is important. The last layer is going to be a softmax. It's not going to be a ReLU. And this will be our Y with a hat. And then we will calculate the error. By subtracting that to our prediction. Y is going to be our prediction. Let's say we expect here a 0, 1, 0. Somebody needs to give you this, okay? And this will give us our error. And from there we will go back. Excuse me, this is wrong. So this is not the prediction, this is the target. So we think it's going to be a 0, 1, 0 vector, and this is the prediction. We want the prediction to be close to the target, of course. So so this is the setting that you would get in the exam, okay? And then you need to start calculating the feed forward. We already know, okay? So we already did this. I will do it faster than -1, 3, 5, 3. Because we have a ReLU, the -1 becomes into a 0, then I have 3, 5, 3. This is our first, and then what we do is we take this and calculate this, and so on. So 0 times 1, 0, -3, plus 5 is 2. Seems to be a 2 there. And 0 times 0, 3, minus 5, minus 2, plus 5. 3 plus 9, gonna be 4. Okay, so we have a 2, 4. We do it again. 3 minus 5 is -2, plus 5 is 3. Oh, wait. 0 times 0 plus 3 times 1 minus 1 times 5 plus 3 times 1 plus 3. This is 0, 3 minus 2 plus 3 is 1 plus 3 is 4. Yeah, it's correct. Because we have a ReLU, the 2 becomes a 2 and the 4 stays a 2. And now I have 2 times 2 plus 0 is 2. Minus 1 is 4, minus 1 is a 3. 2 times 0, 0 plus 8 minus 5 is again a 3. 2 times 1 plus 4 is 2 times 1 is 2 plus 4 is 6 plus 1 is 7. Okay, so the softmax again, if we apply softmax to the vector 3, 3, 7, what we get is following result: 3 divided by 3 plus 3 plus 7, 3 divided by 3 plus 3 plus 7, and 7 divided by 3 plus 3 plus 7, meaning we get 0.23, 0.23, 0.54. Okay, so this is the vector that we inject here. Zero 0.23, 0.23, 0.54. All right. Can you follow so far? Yes, no. This is just the same feed forward that we've been doing, okay? So now let me put the error in a different color. And then the error is 0.23 minus 0. Okay? So 0.23. 0.23 minus 1 minus 0.77. 0.54 minus 0, 0.54. Okay? So now we have the error. And how do we do the back propagation? This was the feed forward. We have done this in several examples, blah, blah, we know. So we're cool. How do we do the back propagation? Sorry. Wait. This is just for the softmax, okay? So now we do the back propagation, and I'm going to explain you step by step what we do so that you don't get lost, because it can be tricky. The first step for the back propagation step 1 is we transpose the error vector being y minus y with a hat minus y. The target is given, anything that is here in black is given to you. So the first thing is that we transpose that vector. This is super easy, as you will see in a second. Okay, so we just go and take the same vector and we put it horizontally. And please, 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 please follow me. So this is the first step. Follow me. If you cannot follow any of the steps, stop me, okay? So we just flip it horizontally. All right? Are you cool? Yes, no, too fast? So I hear nothing, so I guess it's cool. So the second step, and this is something that a lot of people make mistakes in the exam. We perform dot product, even if it's easier than the other thing, we perform a dot product of the transposed error and the output of a previous layer. So the output of previous layer is, in this case, 2 and 4, okay? So what we do is we perform a dot product, and please be very, very careful here. If you don't do this well, the whole system just doesn't work. The dot product is a little bit different than what we did. It's not matrix multiplication, it's easier. Way easier. It's just multiplying elements. So it's 2 times 0.23. Okay? Which is 0.46. This number is 2 times 0.23. And the next number is going to be 2 times minus 0.77. Okay, so minus 1.54. And the next number is going to be 2 times 0.54. So 1.08. And so on. 0.92 minus 3.08 and 2.16. All right? So that's the second step, the dot product. First is transpose. First is transpose. It's prettier. And we like it pretty. Second step is dot product. Okay? So once we have that, we still cannot continue. Okay? We still cannot continue. We need to do a third step, which is also the predicted error. Third step. Multiply the transposed error with weight matrix of current layer. So in order to get the error for the next level, we need to multiply the transposed error and the weight matrix of the, so in this case is multiplying WH23 with error transposed. In reality, this could be called error of matrix number 3. In fact, we should call it like that, yeah, error 3, error 3. Okay? And this is not a dot product, this is a normal multiplication. So we get what we get. Okay, so it's 0.23 times 2 plus minus plus 0.77 plus 1 time 0.54. This turns out to be 1. And then we multiply again, 0.23 times 0 times 2 minus 0.77 plus 1 times 0.54. Turns out to be minus 1. And we call this error 2. This is the third step in the game. Okay? And then we repeat. From then we repeat until we are above. So what I do is I take again the error one minus 1 okay, I multiply it, dot multiplication. Remember, otherwise it's not correct, and otherwise you don't get points. So this is a dot product. And here we do same. 0 times 1 is 0, 0, 3, minus 3, 5, minus 5, 3, minus 3. And then we multiply here again, this one with this one, and we get something like this. One times 1 minus 1 times 0 is 1. 1 times minus 1 minus 1 times minus times 1 is minus 2. 1 times 1 plus 1 is 2. And then 1 times 0 minus 1 is minus 1. This is error 1. we put that up here. That's why we needed the space before. Let's copy it, okay. One minus two, two minus one. And what we magically get, it's a matrix which is going to be like having this format after performing our dot product. Is going to be, so here we again perform a dot product. It's going to be 2 minus 4, 4 minus 2, 1 minus 2, 2 minus 1, 3 minus 6, 6 minus 3. Okay, this is again a dot product. And guess what? This is the new weight matrix H1 updated. And this is the new bias updated. Okay. So we have performed our first backward propagation. And what we do now is we repeat our feed forward. So the step number 4 was to repeat 4. Now is the backward propagation done. And now we repeat our feed forward and backward propagation until the weights are in a minimum, or better said, until the weights deliver a minimum in the cost function. Okay, so the next step would be to get our vector again, 2, 1, 3. I'm going to do it correctly. So again, our vector 2, 1, 3, our input. And now our new bias and weight matrix would be something like something updated, just as we calculated. This is the weight 1H1 star, and this is the P1 star. So this is going to be 1 minus 2 2 minus 1, okay. 1 minus 2, 2 minus 1. And this is going to be 2 minus 4, 4, 2. 2 minus 4, 4, 2. Then 1 minus 2, 2 minus 1, 3 minus 6, 6, 3, okay. And let me move it. Two, 1, 3. When we do our next feed forward, we calculate here the new, because we have updated the weights. Okay. So this is 2 times 2. 2 times 2 plus 1 times 1 plus 3 times 3 plus 1. So 4, 5 plus 9 plus 1 is 15. Okay. And then this is correct. Wait. Do it correctly. Yeah, 15. Then 2 times minus 4 plus 1 times minus 2 plus 3 times minus 6 minus 2 minus 8 minus 2 is minus 10 plus minus 18 is minus 28 minus 30. Then same number in positive, which is 30, and then 2 times 2 minus 1 times 1 plus 3 times 3 minus 1 equals 4, minus 1 is 3, minus 1 is 2 plus 9 is 11. Okay. So if we apply ReLU to this, we get 15, 0, 30, and 11. All right. The next question I'm going to ask you is, what do we put next? Because it's not very clear. What do you put in here? Do I put this? The old weights? Hello? put the old weights. No, I don't put the old weights. I put this, which is the new weight matrix and the new bias that we have calculated. So 0.0353 0.353 WH1 H2 star and then 1 B 2 star and then 0 -3 -5 -3 -1. I perform my, because we are updating the products, okay? I perform my dot, my calculation. 0 times 15 is 0, 3 times 0 is 0, 30 times 5 plus 3 times 11 plus 1 is 150 plus 33, 183, 184. And the other thing is going to be the same, but in negative. Minus 184, which after performing ReLU turns out to be 184.0. Okay. The next is to put again what? This one you should know. What do I need to put there? This, right? Star and B3 star. So I need to put that around here, so I'm getting something like this. And then I need to put 0.46, 0.92, and the bias 0.23 minus 1.54 minus 3.08 minus 0.77, 1.08, 216, 0.54, and what I get is, after multiplication, 184 times 0.46 plus 0.23. Let me do it. (184) times 0.46 plus 0.23. It's going to be 8487. Wait. $84.87. Then 184 times minus 1,54 minus 0.77. Is going to be minus 284.13, and the third is going to be 1.08 times 184 plus 0.54 is 199.26. Okay, so we do the softmax thing on our product on our vector 84.87 minus 284.13, 199.26. Okay. How do we do that? 84.87 plus divided by the sum. Okay, the sum is going to be 84.87 minus 284.13 plus 199.26. 284.13 plus 199.26. Yeah, I guess the softmax goes first, and thus here's some module. So it turns out first everything is positive, otherwise it doesn't work. I guess the first step, if you find negative values, is to get everything positive. And then it works. So you get 284.13 plus 199.26 is 500. $68.26. So if you perform that calculation, what you're gonna get is a vector saying this is 0.15, 0.5, and 0.35. So we plug that in. Duplicate, zack, 0.15, 0.5, 0.35, minus it's not pretty. Zero, 1, 0, which is the target. This is our prediction. And this means we have minus 0.15, minus 0.5, minus 0.35. This is our error. Okay? As you see, our error has gone way smaller, okay, in the module than before. And now we can perform exactly the same backward propagation. And yeah, all the time until we get a constant error, which is a minimized cost. And that's how the cookie crumbles in deep learning.